Hi, I'm Professor Baldwin, and today I'm going to teach you about radicals and how to simplify them. Remember, a radical is written in this format. This is called the nth root of a, where a is our radicand and n is the index. Remember, if you have a square root, that you don't write the number 2 for the index, it's just implied. Now, if you take the nth root of a radicand that's raised to the power of n, you'll get x if n is odd. So if your index and your exponent are odd, 3, 5, 7, and so on. But if you have an even index, we're going to take the absolute value of it because we want the principal nth root, which is non-negative. Think of it this way. If you take the square root of 4, we've always thought of that as positive 2. But 2 squared equals 4 and negative 2 squared equals 4. So technically, the square root of 4 could be a positive 2 or it could be a negative 2. But since we care about the principal nth roots right now, we're only going to look at the positive value. So in the examples and exercises that we're going to do in this section, we're going to assume that all of our variables are positive real numbers. So we're not going to actually use the absolute value bars, but I wanted you to keep that in mind for later on when we start looking at both possible roots of a square root. With radicals, we have these two properties, the product and the quotient property. If we have two radicals that have the exact same index, the product property says that we can multiply the radicands together and put them inside one radical. Likewise, with division, if those two radicals have the same index, we can put them inside one radical symbol and we can do the division inside. So you're going to use these tools to help you simplify. Let's use the product property to help us simplify our first example. We're taking the cube root of c cubed times d to the 6. First, we're going to use the product property to break this up into two separate cube roots. So we have the cube root of c cubed and we have the cube root of d to the power of 6. Now, the cube root of something cubed is just itself. We saw that above. And the next one, the cube root of d to the 6. Well, d to the 6 is the same as d squared times d squared times d squared, right? Or this is the same as taking the cube root of d squared cubed. So this would equal c times d squared, because we take the cube root of something cubed and we're left with just that base. Let's look at a few more examples where we need to simplify the radicals. Remember, we're assuming that all of our variables are positive. So what we're trying to do is pull out as many factors as we can. This one I'll write out in a little more detail so that you can see the visual of it. So the square root of c to the 7th. This is saying c times itself 7 times. Now, when you take the square root of something, our index is 2. So that means we pull these out in groups of 2. So we have one group of 2, two groups of 2, three groups of 2, and then we have a c left over. So for each group, we pull out and represent it as 1. So we have one group, 2 groups, 3 groups, and left inside was that 1c. We simplify these 3 c's on the outside. C times c times c is c cubed times the square root of c. So remember, you're pulling out in groupings of whatever your index is. So as long as your exponent on the inside is larger than your index, you can pull out factors. Let's look at example 2. We're taking the cube root of c to the 7th. So we want groupings of 3's, right? So this would be equal to a c cubed times a c cubed times a c, right? All of those exponents add up to 7. 3 plus 3 plus 1. Now we have one cube root of c that comes out. We have a second cube root of c that comes out, and that lonely c is left inside. I almost forgot my index of 3. And we can simplify that. The two c's on the outside multiply together to be c squared times the cube root of c. Now look at example 3. We're taking the fourth root of c to the 7. So we want to group these in 4s. So if we have a grouping of c to the 4th, then the only other grouping left is c cubed. So here we can only pull one grouping out. So we have c, and we're left with the fourth root of c cubed. Now remember, if you have to write out each term to find those groupings, that's fine. Do that, eventually you're going to get comfortable. Now, example 4, we're taking the 9th root of c to the 7. To do that, we need groupings of 9. Well, we only have 7 c's, so we can't group them any further. So that is as simplified as it gets, the 9th root of c to the 7th. Okay, let's add in some extra terms. In example 5, we have a coefficient of 25. So if we use the product property, we can break up each of these factors into their own radicals. We have the square root of 25 times the square root of a times the square root of b cubed. We know that the square root of 25 is 5. We only have one a in the second square root, so we can't simplify that. Well, b cubed, remember that would be b squared times b, so we can simplify that. We have a b that comes out, and we're left with a b inside the square root. We want to rewrite this. We want all of those radicals on one side together and all of our variables and constants together. So we have 5b times the square root of a times the square root of b. But we can use the product property again to put those two square roots, those radicands, inside of 1 because they have the same index. They're both square roots. So we have 5b times the square root of ab. Now, example 6, notice that we have division. So here we can use that quotient property. So we can either break each of these numerators and denominators up into separate square roots. So we could break this into the square root of p to the 7th over the square root of p to the 4th, and we can simplify that way. Or we could actually use the quotient property for our exponents, which says when you have like bases and division, you subtract the exponent. So the exponent of the numerator minus the exponent of the denominator. So this would be the square root of p cubed. And similar to b cubed, p cubed would be equal to p squared times p. And we take the square root, and we have p times the square root of p. Okay, we multiplied and we divided. Now let's look at how to add and subtract these radicals. Well, in order to add and subtract radicals, you have to have like radicals. And to be like, they have to have the same radicand. So whatever is inside the radical has to be the same. And they have to have the same index. So our radicand in this example is x, and our index is n. As long as those two things are true, we can add and subtract them. We use the distributive property, and we add or subtract the coefficients in front of the radical. Let's look at the first example. We're going to add and subtract these three terms. First, we want to make sure that each of our radicals is as simplified as possible. Well, the only radicals we have are the square root of 10 and the square root of 2. Neither of those contain perfect squares, so that's as simplified as possible. Notice that we have two like radicals. These first two are like. They both have the square root of 10. The index is that it's a square root, and the radicand is 10. So what we're going to do is use the distributive property to subtract, because we're subtracting these two radicals, subtract their coefficients and keep that radical, the square root of 10. And then we have the third radical at the end. So we do 10 minus 8, which is 2, square root of 10, and then plus the square root of 2. So we simplified it. So remember, what you're doing is you're looking at the coefficients of those like radicals, and you're combining those. So we did 10 minus 8. Now look at example 2. Can we simplify anything? I think so. 40 is 4 times 10. 8 is 4 times 2. 25 times 2 gives us 50. And we have some perfect squares there. So let's rewrite each of these terms. The first would be 7 times the square root of 4 times the square root of 10 minus 8, which is the square root of 4 times the square root of 2. And our last term is 4 times the square root of 5 times the square root of 2. Now let's just simplify each little piece. 7 stays the same. Square root of 4 is 2. Remember, we're multiplying these things. Square root of 10, we can't simplify. Subtract. Square root of 4 is 2. And square root of 2 can't simplify. Plus 4 times the square root of 25, which is 5, times the square root of 2. Now we got to continue to simplify, so any coefficients that we can multiply together, we're going to multiply together. The first one we have 7 times 2, so that's 14 times the square root of 10. The second term is already simplified, 2 square root of 2. And the last 4 times 5, which is 20, square root of 2. Now we want to see if we're done. So we're looking to see if we have any like radicals. And we do. The last two terms have square root of 2 in common. So remember, we're paying attention to their coefficients. We have a negative 2 and a positive 20. Negative 2 plus 20 is a positive 18. And we keep the radical square root of 2. And then the very first term, which didn't have a like radical, just stays the same. 14 square root of 10 plus 18 square root of 2. We're doing great, so let's look at an application problem. We're given a rectangle, and we're told that the figure has a perimeter 18 square root of 7 feet, and we need to find the value of x. And then we're going to approximate the value to 1 decimal place. Okay, first we're told perimeter is 18 square root of 7 feet. Well, perimeter is equal to 2 times the length plus 2 times the width, or 2 times length plus width. Let's use this second. Perimeter, we know, is 18 times the square root of 7. And that's equal to 2 times the length plus the width. Our length here is the square root of 175. And our width is x. Now we have this 2 that's being multiplied, so let's get rid of that right away. Let's divide by 2. And when we divide by 2 on the right-hand side, we're just left with the square root of 175 plus x. And on the left, dividing by 2 divides the 18 by 2, right? It's 18 times the square root of 7, divide by 2, we have 9 square root of 7. Okay, we want to be able to combine our like radicals, so we need to see if we can get square root of 175 into a like radical. Well, we know we have 9 square root of 7. So we want to check real quick, is 7 a factor of 175? And it is. 25 times 7 is 175. So we can break the square root of 175 up into the square root of 25 times the square root of 7, and then plus our second term, x. Let's keep our left-hand side. Let's start simplifying the right-hand side. Square root of 25 is 5, and we know that we can't simplify the square root of 7. Okay, we're trying to solve for x, so how do we isolate x here? Yep, subtract 5 square root of 7 from both sides, and you get 4 square root of 7 equals x. Change colors, and I'm going to say that x equals 4 square root of 7, and we need a unit of measurement. That would be feet. Now this would be the exact answer. We're also asked to approximate to 1 decimal place. To do that, you're going to enter 4 square root of 7 into your calculator, and you'll get that this is approximately equal to 10.6 feet. We put these two squiggly lines to say approximately equal to. That's because we had to round that square root of 7 in order to get it down to the 1 decimal place. Thank you for watching. I hope you found this video helpful, and I hope you'll go check out some of my other math videos.